Welcome to Garmin's King Air Autothrottle video series. Our objective is to provide the in-depth knowledge and training you need to safely and efficiently operate the Garmin Autothrottle as it's installed in the King Air. This introductory video will give you an overview of the Autothrottle system and discuss the importance of fully understanding the Autothrottle as part of the automation suite in your aircraft. Garmin's Autothrottle is designed to assist in flight path management, specifically vertical path, speed, and energy management. Autothrottles are designed to be used with or without the flight director and/or autopilot, and with or without vertical navigation, or VNAV. In turboprop aircraft equipped with non-FADEC engines, the autothrottle is designed to operate only the power levers. Propeller control for each phase of flight remains a pilot function. The autothrottle is designed to operate the power levers through their full range, from idle to max power. The autothrottle system can be used throughout all phases of flight, beginning with the takeoff roll all the way to the landing rollout. The autothrottle can operate in speed or torque referenced modes. Garmin's autothrottle system is servo-based, and the power levers are moved by the system. The movement should be monitored visually and/or tactilely by lightly resting a hand on the power levers. Control of the autothrottle is accomplished through keys on the mode controller and a disconnect switch located on each power lever. Annunciation of autothrottle engagement will display in the AFCS status box, while autothrottle modes are displayed at the top of the EIS window above the ITT engine instruments. If use of autothrottle is not warranted or desired, there are multiple ways of disengaging the autothrottle. This includes toggling the AT key on the mode controller, or pressing the AT disconnect switch on either power lever. The autothrottle is intended to reduce the workload for the pilot and allows for more cognitive resources to be used for active threat and error management. During normal and non-normal operations, the autothrottle proves extremely valuable by allowing more focus in conducting procedures with greater accuracy. It's an excellent workload reduction tool for situations when the pilot or crew must maintain aircraft control and conduct non-normal checklists simultaneously. In addition, there are protective functions that Garmin users have enjoyed before, but now can be fully automated, including overspeed protection, underspeed protection, and emergency descent mode. New protective features include autothrottle engine protection and one engine inoperative electronic stability protection when enabled. While the most widespread use and most common application of autothrottle systems is in large transport category aircraft, autothrottle systems are increasingly installed in numerous general aviation airplanes. Over the long successful history of autothrottle systems, the aviation industry has encountered challenges with respect to automated system operations, specifically an understanding of autothrottles. Both Asiana 214 and Emirates 521 provide examples of human performance-related challenges that led to undesired outcomes. In the conclusion of the NTSB report on Asiana 214, one of the contributing factors was identified as the complexities of the autothrottle and autopilot flight director systems, which increased the likelihood of mode error. Most automation-related accidents can be attributed to a breakdown in at least one of four principles. Those principles are an accurate mental model of the flight, both present and future. Mode awareness and monitoring skills are the next layer, which requires the pilot to understand what mode is selected and verify that the aircraft is doing what is asked. Finally, as the pilot in command, if automation is taking the aircraft where you don't want it to go, a pilot must choose the level of automation required to get the aircraft back on track. You may need to lower the level of automation to include disconnecting and hand flying. In addition, successful autothrottle operation is based on a consistent methodology and robust automation management. During the operation of any automation, including autothrottles. A pilot should always check the current modes, set the desired modes, and then verify the desired modes are active or armed. These fundamental principles are aimed at preventing and correcting the possibility of mode confusion, unintended automation states, and automation surprise or startle. We'll now discuss each of these 4 principles in greater detail. Pilots must have an accurate mental model and therefore have a complete and accurate understanding of autothrottle modes, behaviors, characteristics, limitations, and appropriate conditions for use. This creates the accurate mental model required to safely operate the system and allows the pilot to know where the aircraft is and where it's headed. Mode awareness not only means that mode selection must be intentional and disciplined, but that pilots must understand what will happen when a mode is selected. In addition, pilots must develop perception skills that will ensure timely and accurate changes of the selected and automated mode. This skill directly implies developing habit patterns and selecting the modes on the mode controller, followed by scanning the AFCS status box and AT mode annunciations to verify correct mode selection. Pilots are required to develop monitoring skills and have to be aware of the behaviors of the modes and how they interact. So after the AFCS and AT mode annunciations are verified, pilots must monitor the movement of the flight controls and the autothrottle in response to the selected modes. The pilot must assess if the resulting change is as intended. If unintended mode selection or unintended aircraft response is encountered, pilot intervention has to be immediate and accurate to restore the aircraft to the intended flight path and/or energy state. With the knowledge of the previous principles, pilots will choose the level of automation to use. As an example, when automation fails to operate in the intended manner or exhibits a system failure, the pilot must take deliberate and decisive action to restore the aircraft to its intended flight path.
Autothrottle.
This means that hand flying is always an option for the pilot. Now that we've talked about theory, let's go over an example. Let's apply this methodology as we fly the RNAV runway 36 at New Century Airport. Prior to beginning the approach brief assists the pilot in developing an accurate mental model to more effectively manage automation through touchdown. Once cleared for the approach, the pilot needs to have mode awareness and recognize that they are in nav mode, and need to arm approach mode, as well as ensure that the correct speed mode is enabled. One of the most critical phases during the approach is intercepting the glide path, where the pilot will use their monitoring skills to ensure there is a smooth capture and that the aircraft is on the desired speed. After the final approach fix, the pilot may choose it is necessary to adjust the level of automation by changing modes or speed. Garmin autothrottles can remain engaged all the way to the runway. This series will cover the following fundamentals of autothrottle systems: system description and fundamental principles of operation, system modes and annunciations, normal operations and best practices, autothrottle protective functions, and abnormal operations.